Welcome back to buffers. So let's finish up those so that we can get on to titrations. All right, so the last thing we need to talk about is buffering capacity. And we've actually already talked about this, but I just want to kind of tie everything together. So the buffering capacity is the ability of a buffer to hold a relatively constant pH. And remember, the whole purpose of a buffer is to resist changes in pH. And so, how good is that? Well, it depends on two things. It depends on one, how close the pKa was to the pH you needed. Because remember, the closer you are, the better the ratio. And number two, it depends on overall the amounts or the ratio of the acid and the base. Okay, completely generic, but we saw a few of those in the previous calculation. And so we're going to do one more. We're going to do a great big buffer problem. All right, we know that each buffer is unique because it has its own pKa, and so therefore it has a different buffering area. And it will end when either the acid or the conjugate base has been depleted. And that's why the ratio is important, is you want a pretty close to equal concentration of both of them so that you can buffer in both directions. So if you have a ton of acid and not very much base, okay, it's really good in one direction, but it's not in the other. So getting it really close so that those ratios are almost 1 to 1 is ideal. All right, so we're going to go through an entire problem. All right, so let's see. Just making this up. I want a buffer with a pH of 7.30. What I have on my shelf, okay, what you're allowed to use is 0.150 molar of your acid and 0.100 molar of your base. Okay, so we don't know which one it is yet, but whichever one it is, I'm telling you, in the stockroom, there's a bottle of 0.15 molar weak acid and there's a bottle of 0.1 molar wheat base. All right, so my first question is, what is the identity? Okay, who should I choose? Well, I need somebody with a pKa really close to 7.30, really close to 7.30. All right, and if I take the anti-log of that, so 7.30 is equal to the negative log of the Ka multiplied by -1, and then, so the Ka that I'm looking for is 7.3. I'm looking for about 5 times 10 to the -8. All right, now I'm going to go over to my reference sheet, and I am going to limit it to monoprotics. All right, and I know it's sideways for you, but let's see. So I already forgot. It was 5 times 10 to the -8. All right, so if we start at the top, well, that's kind of far away, -10. So I'm looking to see if anybody is at a -8. Okay, that one is, except for it's polyprotic. Ooh, I like that one. Uh, Anybody closer? And don't forget, just because it's in the -8s, don't forget to look just a little bit above and below because I need the one that's the closest. And oh, hey, look at that. This one's nice, but it is polyprotic, so I'm not going to use that one. So I'm going to use hypochlorous acid at 3.5 times 10 to the -8. Okay, so that's how I would choose which one. And so my choice is HClO and ClO minus, and the Ka is, huh, wow, you'd think I could remember from one to the other. I'm looking at my reference sheet. Hypochlorous was 3.5 times 10 to the minus 8. Okay, so that's the one that I think is the closest. Well, what kind of ratio of my weak acid and weak base then do I need? And so the pKa is equal to the negative log of 3.5 times 10 to the minus 8. And so my pKa is 7.46. 7.46, yep. All right, so I'm going to set up my Henderson-Hasselbalch. So if I want 7.30 and I have 7.46, what does my ratio need to be? Now, first off, I'm going to compare. All right, the pH that I want is more acidic than the pH that I have, or the pKa that I have. So I'm going to expect my ratio, okay, my ratio should favor acid, which is in the denominator, so it should be less than 1. Okay, so I wanted to know that before I do my calculation. All right, so 7.3 minus 7.46. So 3. All right, and I have a negative 0.16. Is equal to the log of the base piece over the, whoops, that's supposed to be an HClO over the acid piece. I'm going to take the anti-log to both sides, and my ratio is going to be 0.698, so 0.70. And I did expect a ratio that was less than 1. Okay, so that one looks okay. Okay, there's my ratio, but it does not tell me how much to like measure out of each of those bottles. So I now need to make one that has that ratio, and I am not limited. I could make 1,000 milliliters of it. I could make 100 milliliters of it. So it just depends on how much you want to make. So I'm telling you in this problem, let's start with 100 mils. Okay, so I'm choosing to use 100 mils of the 0.15 molar hypochlorous acid. Okay, so I've set a starting point. Well, I need to know, well, how many moles are in there, because I need to be able to figure out how many moles of base that I need to add. So again, convert out of milliliters and into liters. And then I know for every liter, there's 0.150 moles. So in that 100 milliliters, I have 0.015 moles. Okay, so I know this piece. Okay, so I'm going to plug it in. So if you want to know how much base you need, plug in what you know of the acid and its ratio. And you are going to need 0.0105, and I'm only allowed 2 sig figs, so 0.011. Okay, so I need 0.011 moles of my base piece to go along with my 0.015 moles of my acid piece. And when I put them together, I'm going to have a buffer with a pH of 7.3. Well, how much base do I need? Well, what concentration am I starting with? And I told you to use a 0.1 molar bottle. So, hey, math, if I need 0.011 moles of my chlorate, I know that 0.10 moles is in every liter, and then I'm going to convert out to milliliters. You don't have to convert out to milliliters, but I did, and I'm so sorry that I keep sniffing in your ear. And so that's 105. Now, if you'll notice, I don't get that many sig figs, but right now I'm just going to go with it. No, 110. I did that calculation right, or wrong. Double check, which is why I always double check. Okay, if I want to make my buffer, I need a mole ratio of 0.7. And I know that since I'm starting with 100 mils of my acid, and it's 0.150 molar, that I'm starting with 0.015 moles of my acid, and using that ratio, I needed 0.011 moles of my base, which, if its concentration is 0.1, I need 110 mils of it. So I'm going to add together 100 mils of my 0.150 molar hypochlorous acid and 110 mils of my 0.10 molar sodium hypochlorite, and I'm going to end up with 210 milliliters. Okay, I'm not giving you a concentration because I'd have to dilute those, but I do get 210 milliliters of a buffer at pH 7.30. Okay, that is how I have created my buffer. All right, and so you would choose whatever buffer system is closest to the pH that you want. Right now, let me write a couple notes up here to myself. So this we used 100 milliliters. This we used 110 milliliters. This one was 0.015 moles. And this one was 0.011 moles. All right, so that's what I have. Gonna erase the bottom portion here. Erase a little bit more than that. Okay. So I mix this together and I have a bottle sitting on my shelf of 210 mils of this buffer. Okay, so now we're going to use it. So that first step, I made it. So I made 210 mils of my buffer. All right, I am now going to use it. Now the question is, do I want to use the whole thing or do I want to measure some out? Okay, now for this example, I'm going to use the whole thing. And then in the next example, I'm actually going to measure a specific number out. But for this one, I'm going to just use the whole thing. So here's my 210 milliliter buffer. So inside that 210 milliliter buffer, I have 0.015, and I'm in moles of my acid, and 0.0110 moles of my base. So what is my buffering capacity? Okay, that is my buffering capacity. I have 0.015 moles of my acid and I have 0.011 moles of my base. So that's how much I have that I could use up. So I'm going to be able to put a little bit more base in this buffer than I am acid because I have a little bit more acid to sop it up. All right, so question number 1. I'm going to throw 5 milliliters of, oh, let's say 0.150 molar HCl at it. Okay, so what is my new pH? Well, that begs the question, what are you throwing at it? And it's acid. So who is going to sop up the acid? Is it going to be the weak acid portion or is it going to be the weak base portion? And of course, it's going to be the weak base. And when they react, they're going to make a little bit more of that weak acid. And then that begs the question, well, how much do you have? I have 0.011 moles there still, 0.015 moles there. And then I have to convert this out. And for every liter, I get 0.150 moles. So I added 3075, so 0.12375 moles of strong acid. Do that calculation again. And yes. Okay, so 2375. All right, my question now is, do I have enough of this to sop it all up? And its number is bigger, so the answer is yes. So it's going to use all of the acid I threw at it. But every time I used up a little piece, I converted it into its weak pair. All right, and so how much have I got left? 0.011, 12375, subtract, and I get to keep 3 after, so 0.010. So that's how many moles of my hypochlorite are left, and how much of my HClO is 0.015, 2375, and I get to keep 3 after, so 0.0156. There. Oh, okay. Well, what is my pH right now? The question is, am I still buffered? And the answer is yes, I still have both the weak acid conjugate base pair present. So you just plug it into the Henderson-Hasselbalch. And I already forgot what its pKa was. So 3.5 to the -8. So it was 7.46. Make a little note to myself right there. All right, so 7.46 plus the log of the base piece, which is 0.010, over the acid piece, which is 0.016, 0.01, 0.016. Take the log of that and add it to 7.46. 7.26. All right, did my buffer do its job? And remember, it started, my original pH was 7.30, and even though I added strong acid to it, I'm still at 7.26. So yeah, that buffer did its job. It resisted changes to the pH even when I threw a strong acid at it. Okay, let's just do an example of a base. Let me see, how much should we add? So question B. Let's add 15 milliliters of a 1.5 molar sodium hydroxide solution to it. Okay, so if I throw sodium hydroxide at it, what is going to sop up my sodium hydroxide? Is it going to be the weak acid or is it going to be the conjugate base? Okay, and it is going to turn out to be my weak acid. And remember, and I'm telling you, we're starting fresh, so I haven't used anything yet. It's a whole new problem. And so HClO will sop up that hydroxide. And in consequence, it'll make some water and some conjugate base. And I started with 0.015 moles of that and 0.011 moles of that. And how much sodium hydroxide did I throw at it? So 15, convert to liters. And for every 1 liter, there's 1.50 moles. So I added 0.0225. And 225, so basically 0.023 moles. Okay, my next question. Do I have enough acid to sop up all this base? Do I have enough? And the answer is no. So who's going to get completely used up? It's going to be my poor weak acid. So I'm only going to use up that much of my strong base, but I will make a little bit extra over there. So I'm left with, let me see, I get 1, 2, 3 after 1, 2, 3. So I left with 0.008 of the strong base. And now I have that much of my weak base. Now the question is, am I still buffered? And the answer is no, because I have used up all of my weak acid component. So I cannot use the Henderson-Hasselbalch equation. And I have to ask myself, okay, what is going on in my solution? And right now, I have excess strong base. Sorry, had to cough. All right, so I have excess strong base and I have some weak base. All right, hold on. All right, had to pause again so I could go and cough. All right, back to our question. So are we buffered? No. What's floating around? We still have excess strong base and we have some weak base, but who is going to be controlling the pH? And it is going to be our strong base. And for a strong base, you can just take the negative log. Okay, I have to be fast so I can finish this before I just cough. All right, so I have excess strong base, so I can just take the negative log of it, but I can't take the negative log of a mole. I have to take it of a molarity. So what's my volume right now? All right, back another time. All right, I can't take the negative log of a mole, so I need it of a concentration. And so right now, my hydroxide, I have 0.008 moles of it. And right now I had 210 mils of my original, and I added 15 mils of my base. So my volume right now is 225 mils, so 0.225 liters. So the concentration of my excess strong base is 0.225, is 0.033. And oops, I only get one sig fig. Ow. So really only 0.03 molar. Do that again. And depending on if you carry, it could round up to 0.04. All right. So depending on how you stack your numbers in your calculator, it could come out to be 0.04 of my strong base. Well, maybe I'll make it through this lecture. All right. And if you want the POH, you take the negative log of the concentration, and I'll do the rounded one, the 0.04. And my POH is equal to, let me see, I get 1, so 1 after 1.4, and my pH will be 12.6. Did we expect a basic pH? Well, yes, because I had an overshoot. I have way too much strong base, so I used up my entire buffer, and then I still had strong base left over, and my pH now is 12.6. All right, so we just went over making the buffer, and then we used it. Where should I write this? And then in green, we added acid, and in blue, we added base. And in each case, we then figured out what the pH was. So we created it, and then we used it. All right, so in this case, we use the entire buffer, the entire 210 mils each time. In the next one, I will do an example where you take an aliquot and don't use the entire buffer. Okay, until next time, jolly out.